Hey all. So going to try to do a quick lesson here in relation to mass and matter, which is chapter 18, as you can see there in your textbooks online. So I'm going to quickly run through the main kind of features of this chapter, try and kind of give you a grounding with it, and then you guys can obviously have a good look at it yourselves. And at the end, we'll give you a few questions to work on to see that you kind of understood the stuff. So basically, starts first of all with what is matter. Okay, so in science, it's not like what is the matter with you as opposed to what matter is in a scientific sense. So you see here on the right hand side, matter is anything that occupies space and has mass. That's a very kind of wordy thing to say. Um, Basically, matter is the amount of stuff in something. Now, stuff is very scientific, but it relates to what's in it. Okay, so if there is stuff in something, whether it be a solid, liquid, or a gas, then that is said to have matter. Okay, the mass of it, so how heavy it actually is on an electronic balancer is scales. We measure mass. You've seen this before in kilograms. So kilograms is the metric unit for mass. That can be broken down into grams. So there are 1,000 grams in a kilogram. We can have a ton, which is a 1,000 kilograms. It's important then, I suppose, as well to distinguish between mass and weight, because people say something weighs something, or people say something has a mass of something. The weight is different to the mass because the weight is dependent on the gravitational pull of the Earth or whatever planet you're actually on. Now, we will go into planets and so on next year in second year. We'll talk about Earth and space. But I suppose the key thing to remember here is that if you go to the moon, the gravitational pull of the moon is 6 times less than the gravitational pull on Earth. So as a result of that, your weight would be 6 times less. However, if we can envisage, say, a concrete block, if you have a concrete block on Earth, it has a certain amount of concrete in it. So maybe it is a 1 kilogram block, right, which would be quite small, but 1 kilogram block. If you bring that 1 kilogram block to the moon, it is still a 1 kilogram block. What we say is its matter remains consistent. The amount of stuff in the block is the same. So its mass is the same on Earth as it is on the moon. However, its weight is 6 times less because the gravitational pull pulling it towards the surface of the moon is 6 times less as well. Okay, so it's very important that we kind of distinguish between mass and weight. And really, you guys need to be saying mass all the time when you're talking about how heavy something is. It is incorrect to say weight. Okay? So then the chapter goes on, there's a few little experiments there. They're not hectic, to be honest. But what is important for us then is moving towards the different states of matter. Okay? And I suppose really we should be saying the phases. But states just means what matter looks like. Okay? So there are 3 different states of matter. Now this link here, this is a FET. We've used it before. So it's a FET little kind of an applet. I have the link in this post as well. So you guys will be able to play away with this. Now we're looking here at neon, you can have argon, you can have an oxygen, which is a diatomic molecule, and you can have water, okay? I'll just look at neon, it's easier, because we can envisage the idea of an atom. Now an atom is the smallest part of a substance, okay? If we look here, we can see that basically this is an atom of carbon dioxide here, CO2, so you have 2 oxygens and 1 carbon, okay? When we talk about non-living things, the smallest part of them is an atom. We've spoken already about living things, and living things, the smallest part of them is a cell. So I suppose you can kind of look at non-living things as having cells, but we call them atoms. Okay, now we will delve a lot deeper into what atoms actually are, and underneath atoms they're made up of protons, neutrons, and electrons. But that's a chapter further down the line. For now, you guys just have to see that if you were to take any non-living thing and look really, really closely at it, it would look something like this. Okay, so you'd have your atoms here all tightly packed together. Okay, now we can have atoms in a number of different ways, and depending on the way in which they're connected will lead to whether the state of the actual matter at that time is a solid, liquid, or a gas. So if we look here, when we define a solid in science, we say that solids have a definite shape, they have a definite volume, they cannot be easily compressed, and they cannot flow. What we mean by that is a definite shape means that they take up a certain shape. So if you think of any solid, like a table or television or block of wood, whatever it is, the shape of it doesn't change. Now you can hammer it and maybe smash it and break it up, but I suppose if enough force is put on it, it'll keep its shape. Definite volume is the amount of space that it takes up. Okay, so the volume of it doesn't change. The reason for that is if you look at the atoms, they are very, very tightly packed together. I can't zoom in on this, but they're very, very tightly packed together. Now if I just cool this down, which I can, that's in Kelvin, 3 Celsius. So we can see that this has a specific shape. It's not changing its shape. Now the atoms are still moving. Okay, now again, I should say it has a specific shape. It has a specific volume. Okay, it's taking up a certain amount of space. And you can't compress this. And the reason you can't compress this is because the atoms are already as tightly packed together as they can be. Okay, and what I was saying is that they do have energy. Okay, so just because something is a solid, it doesn't mean that the atoms don't move. They do move, right? But they're not moving a lot. If I start to give it energy, so if I start to bring in heat energy into this, what's going to happen is they're going to start moving more. They start breaking away from each other. And what we get then is a liquid. And we'll notice that the atoms in a liquid have far more energy than they would have had in a solid. Now, they're not moving, like one or two are popping off here, but generally they're staying pretty close together. And what we say is that they're kind of sliding and moving over each other. Okay, so when you envisage a liquid, this is what the atoms are doing within a liquid. Okay, so we say they're loosely packed together, they're sliding over each other. And we mentioned about a solid and the previous thing that they cannot flow, but because in a liquid the atoms have more energy and they're able to kind of move around, we say they can flow. Okay, one thing about a liquid is they do also have a specific volume, but they don't have a specific shape. So they're going to take up the shape of whatever container you decide to put them into. So think of any liquid like water, milk, whatever. Like milk comes in different types of cartons. It will have a different shape in all the different types of cartons because all the different cartons have different shapes. Okay, and then looking, I suppose, what they say in the book in relation to this. So liquids have no definite shape, which makes sense because of the fact that the atoms can move over each other. They have a definite volume. Okay, so even though they're moving over each other, they are still quite tightly packed together. So as a result of that, you're still getting not going to be able to squash them together. They're not easy to compress. You can compress them, so hydraulics would work on the premise of compressing liquids, but they don't really compress them that much, and they are able to flow. Okay, and then finally we have gases themselves. What gases are? So gases have no definite shape, they have no definite volume, they can be easily compressed and they can flow. Okay, so if we look at a gas from the context of PhET, we can see here, there is the idea of a gas. Okay, so the atoms are moving all over the place. Okay, so what they do is actually they move to fill up the whole volume of the container that they're in. You'll notice that there are lots of energy, so they're moving around, and there's lots of space between the atoms as well. And this is important because that allows a gas to be compressed. So you can see here then, if I take another container and just put a gas into it here like this, give it an opportunity to move around. So there's our gas moving around. Again, you'll notice that the gas will keep moving, the atoms have lots and lots of energy and they'll keep moving to take up all the space of the container. But because there's space between them, I can actually close this down here and force them into a smaller space. So in other words, that's me compressing the gas. Okay, so it's important that we know the difference between solids, liquids and gases and what they stand for in the context of matter. So that's what you gotta have to, I suppose, be aware of. Then moving forward with gases themselves, then actually one last thing I need to mention on this, skipping there. So look at the idea of diffusion. Now diffusion is when gases mix together. Now the best way I can explain this is, I'm sure now you're all at home at the moment and your mums and dads are making you big fry-ups every single morning. But if you're down in your bedroom and your bedroom is, say, a bit away from the kitchen and the fry is going, the smell of the fry will actually make its way down to your bedroom. The reason for that is because gas particles, if they're released into a space, will spread out to fill up that space. Okay, so if you look here on the left hand side, we have a certain type of particle, and on the right hand side, we have another type of a particle. Same thing would apply here with an aerosol can or something like that, right? Or maybe a stink bomb, whatever. If we imagine that this is just the normal fresh air here, and we'll say this is the smell, whether it be an aerosol can or a stink bomb or the smell of the fry. If we release the smell in the room, what happens is these particles, because they're in constant motion, will start to move into the space, and the gases will start to mix together. And you'll notice that the red is starting to move across this way, okay, and the blue the opposite way. So the two gases are diffusing into each other. So this is showing that the smell moving across. And like say, if you're in one corner of a room and you let an aerosol go, or maybe a bit of aftershave or whatever else, eventually that smell will make its way through the whole room. So we call that movement of gases through other gases diffusion. The same thing happens with liquids. If you have MiWadi and water, if you put a small bit of MiWadi into your water, eventually all of the MiWadi, so it says orange MiWadi, the water will eventually turn completely orange. Okay, so liquids will also diffuse through other liquids. So diffusion is just the movement of the particles and mixing together. Okay. The last thing then on this is relation to the changes of state. So when you change a solid to a liquid to a gas, and then change a gas to a liquid to a solid. Now, when you think of these, you really have to think of water. Okay, so water is the one. So when we change a solid, in this case ice, if you take ice and you heat it, ice will turn from solid ice into liquid water, and we call that process melting. Any solid that turns into a liquid, the process is melting. And when you take a liquid, so in this case liquid water, and you heat it even further, like in a kettle, what happens is it turns into steam, and we call that boiling or evaporating. Either or is fine. Okay. In both of those, what you're doing is you're adding heat energy. So you're giving the particles more energy so they can split up and break up to go from a solid to a liquid to a gas. The reverse of that then is if you have a gas, so in this case steam, because we're using water as our example, that condenses down into liquid water. So when you think of in the evening time, if you're cooking your dinner, you look at the windows, when the steam from, say, cooking your potatoes hits the window, because the window's cold, it forms this kind of a fog on the window. That is the steam or the water vapor in the air hitting the cold window and turning back into liquid water. And finally then your liquid water turns, if you keep cooling it, will turn into a solid because it loses all of its energy, and we call that freezing. So we're using water as our example of changing solids into liquids into gases, and also from gases into liquids into solids. But it's really important that the terms melting, evaporating, condensing and freezing all relate to any substance changing state. So when any solid changes into liquid, we call it melting. When any liquid changes into gas, we call it evaporating. When any gas changes into liquid, we call it condensing. When any liquid changes into a solid, we call it freezing. Okay, so I think I've hit on all the key points there. So if you have any questions related to this, please get on to me through Schoology, and I'll hopefully get back to you as quickly as I can. Okay guys, take care, bye bye.